Next thing we're going to solve for in this circuit is the power values. In this case, we're going to be looking for the individual powers and also total power and making a comparison between the two. In this case, in order to solve for power, we got to use our Watts formula, which is E times I. Power is equal to the voltage times the current. But since we're solving for the individual components, we need to use the values of those components as well. So in this case, since it is a series circuit, I have to use the total current and multiply it by the voltage drop at resistor number 1. In this case, I get 0.0228 times 1.71, and it gives me a wattage value of 0.0389. Do the same thing for power at resistor number 2, gives us 0.0779 watts. Same thing for power at resistor number 3, and it gives us 0.1559 watts. Okay, so these are your individual powers. Keep in mind that since we did round it off the current values, these voltage values are also rounded off. So the wattage values are not going to be exactly the same when we go to make a comparison between total power using Watt's law and solving for total power using the sum of the individual powers. So if we look over here, here's our total power. Take your total voltage times your total current, and we get a total wattage of 0.2736 watts. 12 times 0.0228 gives us this value. And if we solve for total power using the individual powers, we can see that we're off roughly by, I don't know, 9 watts. Okay, but it's still very close, still very comparable, 0.2727 watts using this method to solve for our total power compared to using the Watt's law formula. Okay, and this is how you solve for total power.